Hi, my name is Brittany Davis. I'm a food technologist with JLA International. Today I will be presenting measurements of high oleic purity in peanut lots using rapid single kernel near-infrared reflectance spectroscopy. This was a joint effort with JLA IEH, Hershey, North Carolina State University, and QualySense. I would like to thank my colleagues for their contributions. High oleic peanuts are unique in regards to their oil chemistry, more specifically their fatty acid composition. This quality gives high oleic peanuts improved post-roast shelf life in comparison to conventional peanuts. Due to this desired quality, it is important to maintain a certain level of purity in these peanut lots. Purity is defined as the frequency of true high oleic peanuts in a bulk lot. High oleic lots can become contaminated with that of normal oleic or conventional peanuts. This can result from unintentional mixing at the breeder or seed level, improper handling through the production chain, or from the presence of physiologically immature high oleic kernels. In whole nut applications, given the format of these products, they are more vulnerable to oxidation, and the presence of just a few rancid kernels can ruin the overall experience for the consumer. In order to optimize the flavor and shelf life of these products, it is critical to achieve a certain level of high oleic purity. 100% purity being the goal, of course, but the higher this purity, the better. To understand high oleic purity, the industry monitors its lots by taking a sample of 10 to 100 kernels to estimate the purity of a potential high oleic lot. Methods for these kernel checks include refractive index, gas chromatography, or near-infrared measurements, among others. The current methods used are time-consuming and expensive. Some of these methods also require destruction of the sample. As with other types of measurements, purity assessments are affected by changes in the sampling plan. Specifically, by increasing the sample size, we can improve the estimations made about true lot purity. The current best method of using 100 kernels to check purity is limited in practical effectiveness. For the current study, a new technology is assessed to measure the purity of potential high oleic peanut lots. This new technology is called the Qsorter Explorer. The Qsorter is a high-speed, single-kernel measurement and sorting device. It is non-destructive to the sample, and it is a unique technology in that it utilizes a vacuum belt delivery system coupled with simultaneous near-infrared spectrophotometer and vision measurements. For the current study, individual peanuts were analyzed at 20 kernels per second. Here's a picture of the Qsorter. First, a sorting property is selected using the computer program. For this study, we selected oleic acid. A batch of peanuts is loaded into the hopper. The air pump below provides a vacuum system to pull kernels onto the unique belt delivery system, which allows for fixed position delivery of the individual kernels to the vision and NIR systems. The kernels first pass through the vision system, where a 3D image, like the one you see here, is acquired. The kernels then pass through the NIR, where biochemical measurements are taken. Directly after this, using machine learning and a computer algorithm, a quick decision is made by the device to then sort the kernel into the corresponding bin, based on the desired property and selected threshold. Since we sorted using the property of oleic acid, conventional or normal oleic peanuts were sorted into bin 3, high oleic peanuts to bin 2, and unclassified kernels to bin 1. This is where peanuts that are not properly sensed are sent, along with any foreign material that may have been present. While peanuts for this study were sorted for oleic acid at a desired threshold, all other measurements for each individual kernel are recorded and returned in a data set, like the one you see here. Before starting the study, the device went through a validation process to assess the precision and accuracy of the predictions made. Sets of peanuts, primarily runners, totaling 160 kernels, were selected for validation and scanned using the NIR 3 times per kernel. These kernels covered a range of oil chemistry, crop year, market type, and grade. Kernels were scanned using the Qsorter. Then the individual kernels were captured in vials and subjected to gas chromatography analysis. We were able to then compare the Qsorter predictions to the reference values obtained from the GC. Here in this graph, we have the results of the validation process, with the predicted oleic acid values from the Qsorter on the y-axis, the actual oleic acid values from the GC on the x-axis. With the variety of kernels selected, the validation set covered a wide range of oleic acid. Conventional peanuts, seen in blue, ranged from 46 to 65% oleic acid. Mid-oleic peanuts in red were from 66 to 72. And high oleic peanuts, seen in green, ranged from 75 to 83% oleic acid. As you can see, the Qsorter prediction showed a linear fit with the reference values, and a R-squared of 0.78. Our root mean square error of prediction was calculated to be 6.35. For this study, we made 7 different mini lots varying in contamination rate by hand mixing a certain amount of conventional peanuts into high oleic peanuts. The mini lots weighed 4,200 grams each and were made into 7 different contamination rates of 0, 5, 10, 20, 30, 50, and 100% contamination. This was done of 3 grades, including jumbo, medium, and number 1 peanuts. Each mini lot was sampled at 500 grams with 8 repetitions for each contamination rate. This is a summary of the experimental analysis, including the number of kernels analyzed for each mini lot. Equivalent masses were analyzed for each size class. However, due to expected kernel size differences between the 3 grades, we see a difference in kernel counts. For the jumbo size class, we analyzed around 5,300 kernels, medium around 6,400, and number 1 around 8,500 kernels. We can see that as the contamination increased between the different mixes, the average oleic acid and purity decreased. Given the established range of the populations and the measurement error observed in the instrument, we set a cutoff or a threshold of 66.5% oleic acid. This was done to minimize the overall purity misclassifications. The jumbo lots tended to have higher average oleic acid and purity due to the tendency of these kernels to be more mature. As you can see by the provided histograms, all 3 grades, jumbo, medium, number 1, showed similar behavior in predicted oleic acid values for all mixes. The solid line you see in each graph is the 66.5% threshold discussed previously. This depiction also shows us the response in oleic acid measurements as the contamination rate changes. The 0% contamination, or the 100% high oleic lot, and the 100% contamination, or 100% conventional lot, show 2 distinct normal populations. Through these histograms, and as the contamination rate increases from 0 to 50%, we see this bimodal response due to the presence of both normal and high oleic peanuts. For this study, we also examined the effects of sample sizes on purity measurements. This was done by leveling out all of the grades to an even 5,000 kernels each, and then dividing into sets of 10, 50, 100, and 500 kernels. We then compared the predicted values using binomial statistics. Here we have purity measurements broken down by sample size for each mix. In this image, we chose to share the medium grade data, as the other grades also showed similar responses. On the y-axis, we have the calculated purity measurements, and on the x-axis, we have the different sample sizes of 10, 50, 100, and 500 kernels for each mix or contamination rate. We were able to see that as the sample size increased, the variance in purity measurements decreased dramatically. Also, as the contamination rate gets closer to this 50% mix, we see that the variance in purity measurements gets larger. If we focus on one of the individual mixes, let's take this 20% contamination mix for example. We see that with the repeated measures of the 10 kernel count sample size, the variation in purity measurements is quite large, ranging from 30 all the way to 100% purity. Whereas if we look at the repeated measures for the 500 kernel count sample size, we see a dramatic decrease in this variation between purity measurements, ranging only from 75 to 80% purity. Larger sample sizes give a much better estimation of the purity, since the values are closer to that of the expected value of 20% contamination or 80% purity. As stated previously, this variation in purity measurements associated with sample size can be seen across all of the mixes. Binomial statistics can be used to explain this oleic purity data. Since we are answering this yes-no question of whether or not a kernel is high oleic or conventional. In this figure, we have our variance about the purity measurements on the y-axis. The average purity measurements are represented on the x-axis. We see a parabolic response as the lot purity increases from 0 to 100, with a max in variation at the 50% contamination or 50% purity. The plus symbols seen here represent the theoretical variances predicted by binomial statistics for these sample sizes. We can see that our data fits this theory quite well. As discussed, we were able to see from this study that sample size directly impacts oleic purity measurements. The larger the sample size, the less variability and better estimations can be made of the true lot purity. The data represented in purity measurements is well described by theoretical binomial statistics. We can then use this statistical approach to create OC curves, or operating characteristic curves, and use them for best sourcing potential high oleic peanut lots according to the needs of the industry. The device introduced here, the Qsorter Explorer, was able to predict lot purity through rapid single kernel measurements at 20 kernels per second. Depending on the peanut size, this device is capable of processing 25 kilograms per hour, allowing for larger measurements in a short period of time. This technology will improve the effectiveness of identifying true high oleic lots. While we did not discuss it here, kernels can also be physically sorted in real time, allowing breeders or the seed industry to purify small lots of peanut seed. We hope that this presentation gave you a good insight into this new technology and how it can be used to assess lot purity, among other measurements to assess overall lot quality. Thank you.